Okay. So a very good day once again. So
Okay.
we'll just run through quickly and see how far we'll be able to take the class. Just like I mentioned earlier, we'll talk about a couple of error control codes, but the major classifications we'll talk about will be the block codes and the convolutional codes. I already made mention that for the block codes, well, we'll talk about the Hamming codes. Then outside the Hamming codes, there are some other codes we'll still make mention of. Then we'll talk about the cyclic codes. Then we'll talk about the Bose-Konduri-Hokwegem code, which is the BCH. And then, though it's a binary code, that's the BCH, but a type of the BCH that is non-binary, which is the Rich-Solomon code. We'll just mention their characteristics. Just like I mentioned earlier, we can actually find, useful information in some interesting textbooks on them. And then, well, in as much as we want to encode using a particular algorithm for error control, we also want to decode. So the system of decoding is called syndrome. Okay, so we call it syndrome decoding. Yeah, so that's how we are able to recover this, recover the transmitted code. And now we are going to see how it is designed. Now, for us to be able to get the code words which are encoded or transmitted, the encoder output, we need a generator matrix, right?
Yes.
Remember. And now, if we have that in the encoder, then in the receiver, then we should have something to decode it. So there we are going to be having a parity check matrix. Okay.
Okay, sir.
So let's move this. So it means that here we have the encoder. So we have the symbol coming in here. Now it's expected to go through the channel, right? And then we have the decoder. So it means that, recall that we said the code word has a block length of n, right? So it means that the encoder output, so let's correct this. Let's just take this off, for instance, for the sake of convention. So this is the random variable, okay? It's more like the distribution, the symbols. Say symbol K, okay? The message symbol, okay? So once this symbol K goes into the encoder, then we know that the encoder is going to add some parity, right? In the parity, in the encoder will add some parity so that here it becomes Sn, such that at this point, the parity is going to be some Sn minus K, right? Where n minus K is the parity, where K is the message symbol, such that this length n is not going to be n minus K, okay? K rather, this is K, n minus K. This is K. So this is K message bit, and this is the parity. So we have the message bit, and then we have the parity check bit. So this put together is the encoder, okay? And we're made to understand that the longer this, the block length n, the more robust, if you remember what we're still describing the information theoretic perspective, the more robust this code word will be in terms of handling channel impact or effect, okay? Now, for us to be able to get this code word, it means that there's something we call the generator matrix, okay? In this encoder. This is what will generate all the possible code words in the code book. All the possible code words. Okay. Now, in the decoder, we are expected to recover the transmitted symbol so that R, it will be the same as S of K, right? So in other words, we are going to extract the transmitted message symbol from the encoded symbol, which is the code word, the encoder output, SN. So what we now want to do is that there must be a system to recover what was transmitted based on the generator matrix. And what we now call that is the parity check matrix. Parity check matrix, which is used for syndrome decoding. So this we denote as G, as we will see shortly, and this we denote as H. Okay. Now, I'm just trying to run through a few things. So in other words, recall that for us to be able to get our code word, we have the generator matrix acting on the message symbol, okay? So technically, we now have to provide a formulation for this expression. So we are going to do that right quick. And then we are also going to compare this generator matrix with the parity check matrix, which will help us in decoding what was transmitted. And once we do that, then we are done, because when the syndrome is 0, it means there is no error in the received message or sequence. But should there be error, then it means that what was transmitted is not what was received. Because let's say, okay, well, I'm just giving a brief background. So now let's say here the generator matrix is described as the identity matrix and the parity check matrix. Now, the parity check matrix is more like the inverse of this exercise, okay? And then we now have to take the transpose of this particular operation. And once we take the transpose of this particular operation and then include the identity matrix, then we'll have this, such that we now have this as the transpose of the parity check matrix and the identity matrix. Now you observe that there's something common with these, with the generator matrix and the parity check matrix. And that is the, and that is this parity P. Okay. And then once we have this, oftentimes some tests also put it the other way, okay? At times we see that G is given as a parity identity matrix, and then H will be identity matrix, the transpose, okay? Now, whichever way, there's no problem. But where I'm going to is this. The code word will now be generated based on the message symbol. So there, we now multiply that with the generator matrix to get each code word. So we are going to see this shortly, okay? And then at the end of the day, when we have the parity check matrix, then the parity bits also follows directly, because for the parity bits, we now have to multiply. You know, here we are using the generator matrix. Then we now have to multiply the message bit with the parity check matrix. And then we will now be able to get the parity bits. So once we have the parity bits, then we'll be able to establish our syndrome, as you'll see shortly, because all of those will take effect or take place right at the receiver. Okay? Now, once this is done, you now see that the syndrome, we now have to multiply the received symbol with the transpose of the parity check matrix. And once we do that, we will now be able to decode what was transmitted and then tell if what we received is in error or not. It's that simple. It's that simple. And once it's in error, then we'll also be able to tell. Then run a few analyses and then come up with our assumptions, and then we are good to go. But for us to be able to do that, there is equally the notation we need to establish, you know, and it is very, 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 very important. The board is a little messy, so let's use a different color. That once we multiply the generator matrix and the transpose of the parity check matrix, is going to give us the same as multiplying the generator matrix and the parity check matrix and the transpose of the generator matrix. This should give us a 0. Okay. Now recall I said this could be either way. So if we define my generator matrix this way, then my parity check matrix will be described this way. And if I should describe my generator matrix this way, then my parity check matrix will be described this way. Okay? You will see the position of the identity matrix in both cases. So that when we take the transpose of one and multiply by the other, it will be 0. We are going to test this so that we see how, because this information helps us in syndrome decoding, as we will see shortly. Okay? Because if this is true, then we can now compare what we receive at the receiver. Because this is, we are actually trying to do error control. Okay? So we want to do error control. So at the receiver, what we receive, let's follow up. At the receiver, because this is the channel, so the channel effect will give us some error. Okay? And now we know we are also going to receive the code word. So here we are going to have the code word plus this error. So this is what is going to come out. So after decoding or undecoding, what we receive will be C plus this error, the code word. Okay? And now we know that the syndrome is what we receive times this, the transpose of the parity check matrix. And then we can do the analysis. It's that simple. So if we do the analysis, so we see that if we substitute R into this, so it means that here the syndrome will be the same as C plus E HT, which is C H transpose plus E H transpose. Now, what is C? Is the message bit times the generator matrix. So from this, the syndrome will now be, if we substitute for that, M G H transpose plus E H transpose. Remember, G H transpose is the same as 0. So this should give us 0. And once that gives us 0, what is remaining is the error function. So it means that if this is also equal to 0, then it means there is no error. So should we now have a value coming based on this, then we now know that there is an error. So by the time we perform syndrome decoding, if we get a non-zero value after syndrome decoding, we know that what we received is an error. Is that clear? I'd love to get your feedback, please. Is that clear?
Yes, sir.
Okay, so if that is clear, so we have been able to establish that right in the decoder, we do syndrome decoding here. And that's where we have our parity check matrix, H. And in the encoder, we have the generator matrix, G, to generate the code words. And depending on the sequence, that's K, that will tell the number of code words in the code book. So if K, for instance, is 2, then we know 2 to the power of 2 is equal to 4. So we have 4 code words in the code book because we are going to be dealing with NK codes, right? NK block codes. That's what we are going to be dealing with. Okay. So now everything I just mentioned is all about block codes. And I'll say, well, we're done, but well, for formality's sake, let us run through. So when we talk about error control coding, the fundamental goal is error control so as to maximize the reliability of the transmission process within certain constraints, okay? So when we say error control coding, we want to ensure reliability of the transmission process under certain constraints. And what are those constraints? The first is signal power. Another constraint is system bandwidth. Another constraint is complexity of the circuit. So these are the constraints. Now, should we increase the power? There's every tendency that we'll be able to recover a signal because the signal power is higher than the noise power. So it means P squared is greater than sigma squared, which is the noise variance. So here we can take the signal to noise ratio, right? So once this is high enough, then we are good to go. But it's at a cost. For us to be able to do this, then we'll have to sacrifice our bandwidth and also the complexity of the circuit to achieve this. Then, should we design such a system that will transmit at a very high power, then we'll have to figure out the battery lifespan of our devices because they will drain faster than necessary. So we want to transmit at low power. So it's just a trade-off. Then bandwidth. Now, the channel bandwidth is of interest to us because we are dealing with narrow band systems, okay? Or better still, band limited channels, which we already discussed, and we know the capacity. And coming from Shannon, then the rate of transmission should be less than that capacity for error-free transmission. So we now come to the complexity. Now, the circuit that we need to arrive at this system should not be altogether complicated. But should we desire to correct for some kinds of errors beyond 1 bit, we want to correct for burst errors and the likes, know that we have to deal with that complexity, because we'll now have to move from combinational circuits, from combinational circuits to sequential circuits. And that's how we move from block codes, where we use combinational circuits, to convolutional codes, where we use sequential circuits. Because for block codes, there is no memory, but for convolutional codes, yeah, we have memory because we use shift registers, okay? Yeah, we use shift registers. So conventionally, error control coding is used to reduce the transmitter power and the size of antennas in view of obtaining specified probability of error. So that's why we want to do error control coding. We want to transmit at a very low power, at low power. And then we also want to transmit using small sized antennas at specified probability of error. So the need for error control coding becomes very important, so that no matter the noise within the channel, we should be able to maintain the integrity of what was transmitted. And the only way we want to do that could either be through automatic repeat request or forward error correction, okay? So, and the idea, regardless of these two techniques, is to add redundancy. That's how we do this. So once we add redundancy, we may not have to bother about the power of transmission, okay? And although this further results in a lower data transmission rate, because we are increasing the redundancy, we are actually reducing the actual usable bits, okay? So I want to transmit 101, but now I have, this is my message bit K, and I have 00010101101. Then these are my redundant bits. So this is actually using up the bandwidth. So at the end of the day, this is my data rate, because my data rate is not going to be, my rate is going to be my message bit over the block length. So this will now be 3 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 over 14. So you see that my rate, the rate is reducing. Unlike when I have more of these as my message bit and just few redundant bits, so the rate will be 14 over 3. So I'll have higher rates. Okay, so introducing redundancy into the message bit so as to correct for errors or to make it more robust or resilient against channel effect or errors actually lowers the data transmission rate. Okay, now or alternatively, if it's uncoded, then we increase the channel bandwidth. Okay, but an alternative for what's it called now? Band limited channels is to use the Trellis codes, which we'll talk about. Okay, we're going to talk about them, and because they do not require the sacrifice of either data rate or bandwidth, they are more robust. So when we talk about convolutional codes, then we are going to talk about the Trellis codes, okay? Because we use them for maximum likelihood decoding. Okay, only that the circuitry is, quite complex, okay? So there, we don't have to worry about all of these power bandwidth issues or data rate issues, but the complexity, okay? So now, this brings us to basic types of block codes or basic types of error control codes. Okay, so let's say basic types of block codes. Sorry, not block codes, basic type of codes or error control codes. So we have one, block codes, and the second is convolution or convolutional codes, as some may call it. Okay. And the major difference between the two is the memory in the encoder. Okay, so the block codes, for block code, they do not have memory, in the encoder. Okay, but for convolution codes, they have memory. Okay, have memory. Encoder. So I remember when we just started in our earliest lectures of first lecture or second, I can't really remember. We made mention of this. So if we have to look at this from the electronics perspective, we already know if we have to design circuits that do not have memory, the next thing that comes to mind as sequential is, or better, no, sorry, is combinational circuit. Yeah, combinational, because they do not have memory. So what comes to mind is combinational logic, right? Logic circuit. And here we have our regular AND gates, NAND gates, right? For switching, okay? So when you do your digital circuit design, so you see how to use your NAND gates for switching, okay? So with that, you're able to generate your zeros and ones, okay? And with that, we are able to manipulate our way through and design block codes. But when we now say a circuit have memory, so the next thing that comes to mind, should we attempt to realize this in practical terms, then we have to introduce sequential logic. And here we have flip-flops. And we can now begin to talk about registers, because with the flip-flop, we can hold a bit in a certain state, then while we do our reset and set, and all of that. So with this, we have memory, okay? We have memory once we introduce the flip-flops. Okay, so it means that for the block codes, each encoding operation only depends on the current input message and is independent of previous encodings, okay? So once we feed in our one, then we know what we are going to get instantaneously. But for our convolutional codes, once we input our one, let's assume we have about 3 registers here. Let's assume the original initial state is 0, 0, 0. So if this is the input, should we feed in a 0? So it means that, okay, let's use a different color so we are able to visualize. So should we feed in a 0? So it means that once the 0 gets in here, the original bit that was here, the black bit, moves to this point, and the next moves to this, then this bit that is here is discarded, is dropped. So we'll now understand this when we use a 1, okay? Now, so let's assume this now becomes the initial state where we have 3 shift registers, 0, 0, and now we have this. Then we now feed in the input 1. So it means that this is going to be knocked off, and then we now have 1 at this point. This one is now at this point. Then the original 0 that was here moves to the next shift register, and this 0 moves to this, and the 0 that was here originally is dropped. And now, if we now have this as our initial state, which is 1, 0, 1, and we feed in a 0, so that 0 comes in here, this 1 moves to the next shift register, and this 0 moves to the next. So you now see that here we are able to hold on to the previous bits while we take in new bits. So hence, memory, the memory has memory. Okay. So we are going to see them also. Now, I already mentioned that the error control code can be achieved by either using forward error correction, called FEC effect, or automatic repeat request, just ARQ, or it could be hybrid. That's hybrid ARQ, which is HARQ hack. Okay, so this combines these 2 features. Okay. But you should note that the ARQ uses a feedback. Okay, that is why it could request retransmission. Okay, so it usually requests retransmission through the feedback loop. Okay, but for the forward error correction, it uses just redundancy. Okay, at the receiver. This also uses redundancy, but the difference is that it calls for retransmission should there be an error. Why this uses redundancy? To correct the errors. Okay. Now, if that is clear, then we'll just move on to look at some other interesting details. So I really don't want to go through what we have in the other videos, but you could look them up. So we already know what a code word is, okay? That it is the encoded block of n bits, okay? I just mentioned it. So this is n bits, such that it combines both the message bit and the parity bit, right? And n is the block length, right? Where k is the message bit. Then n minus k is the redundant or parity check bit. And then the rate of this code, which we call the code rate, I mean, is the ratio of the message bit k to the block length, okay? And then we have the channel data rate. Channel data rate which is the output rate, which is the same as N over K times RS, where this is the encoder rate, okay? The input encoder rate, why this is the output, okay? Then we also have the code efficiency, and the code efficiency is equivalent to the code rate, okay? Because it's the message bits in the block over the transmitted bits of that block. Then I also remember that in our previous lecture, we made mention of systematic codes, okay? And there, we mentioned that when the message bit is distinct relative to the parity check bit, then we say this is a systematic code. And most of the codes we are going to be playing with are going to be systematic codes. While the non-systematic code is one in which the n-bit code word may not contain any information bit explicitly. It's all modeled up together. So now, with this, we can now move on to linear block codes. So let us look at a few linear block codes, and then look up the convolutional codes, then that should be it. So the first thing that comes to mind is, why is it linear? Why is it linear? Why linear? So, well, we'll deal with the word linear, okay? Because we already made mention of that, such that if I should operate now, when we talked about the Galois fields, so if I should have some symbols, x1, s2, s3, s4, all the way to sn, in this collection, in this is set. Now, should I operate on this code, on these symbols, say x plus x1 plus s3. Now, should this give me s2? So it means that these are linear codes, because any operation on them still gives me a code that is within this set. Well, we'll come to that and explain that, you know, more intuitively. But let's leave that for now, and then talk about the block code itself. So here, a block code of, say, length n and 2 to the k code words for which k is the message bit is said to be an NK code if and only if each 2 to the k code words forms a k-dimensional subspace of subvectors of all the n-tuple over the Galois field. So in other words, we can say that a binary block code, a binary block code is linear if and only if the modulo 2 addition of 2 code words is also a code word, which I just explained, okay? So what if we try to play with two code words, for instance, in that sequence, in the code book rather, and then realize that it does not generate a code word in that code book, then automatically we know that it is not a linear block code. Okay, so this is very important, and I would love you to take note of that. So now, if that is clear, then I will now move on to what we described earlier. Okay, so it means that should we, for instance, now have a code that is considered to be linear, since the sum of any two of those code words produces another code word, then we now say that that property for which the sum or the modulo 2 addition of two code words forms another code word is called closure. Okay? Closure. And in our, excuse me, please. So in our previous note, we made mention that if we have M message bits, for instance, and then this is M message bits, and then B parity bits, then the code vector C, code vector, as some will call it code word, is going to be given as the parity bits relative to the message bits. But in the matrix form, the parity bit B is the same as MP, where P, in this case, P is the n by n minus k coefficient matrix. And this matrix is defined as P being the same as P I sub j. Okay? And you already know, so for the matrix, we could populate the matrix, say P00, P01, all the way, P10, P11, all the way, just that way, right? So it's a matrix. So we rather say P I sub j. And now the code word will now be the same as M times the parity with an identity matrix, where I sub k is the identity matrix. So going by this, the generator matrix will now give us this expression, which is P I sub k. Okay. Now, this is very simple. Now, since this is what we have, let's assume, let's do a little analysis. So from this, we have C is equal to, let's substitute this into this, MP, M, right? So if we bring M out, so this is going to give us M into bracket P, I. Isn't it? Because this is B, and the code word is given as this. So if we substitute the parity into this expression, so we're going to have MP, M. And once we bring this out, so this will be M into square bracket P, then dot I. So where this is the generator matrix that generates this code word given this. So that is how we have this expression for the generator matrix, which I already pointed out earlier. Okay? And intuitively, by the same measure, we see that the parity check matrix is now the same as the identity matrix times the transpose of the parity check matrix. So if this is true, because now recall that in a transmission, in a system channel, we have a communication channel. This is a communication channel. We transmit X over a channel, and we're expected to receive Y. Recall that we made mention that the act of recovery is an inverse operation, right? It's an inverse operation. Hence, the parity check matrix, since the parity check matrix rather is used for decoding, it is going to be an inverse operation of the generator matrix. Okay? Hence, this operation, which is the inverse operation of this. Okay? The inverse operation of this, which is now I E transpose. So if that is true, then it means that if I have A at this end, then on the other side, I have 1 over A as a means of recovering this. Then A times 1 over A, in this case, is supposed to give me 1, right? But should I now take this in the binary notation? This is not binary, okay? This is non-binary. But should I now consider this operation in the binary field? Recall our Galois field. Now, any operation for which we have the similar operation, this should give me 0. And the same with this. And this equal to 0. And then, should I take a reciprocal of this, what am I going to get? So we have to review our Galois field now. Now, let us now take things further to validate this, such that the parity check matrix times the transpose of the generator matrix is the same as the generator matrix times the transpose of the parity check matrix is equal to 0. But the bottom line is, how true is this? Okay, let us test this. Let's see if this is true with a simple example. So let us assume we have P, the parity matrix, to be 0, 1, 1, 1, 1, 0, 1, 0, 1. So it means that the transpose of this is going to be, the row becomes the column, that 0, 1, 1 becomes 0, 1, 1, becomes the column here. The row here, 1, 1, 0 becomes 1, 1, 0. And the row here becomes the column, the row here becomes the column here, which is 1, 0, 1. So we have the transpose. Now, we have that the generator matrix is the parity with the identity matrix, which we already showed, we proved that. So in other words, I have to take this 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, 1. Then the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So we've added the identity matrix. And the same thing here, we have the parity check matrix is the same as the identity matrix and the transpose of this. And then we have the identity matrix will be 1, 0, 0, 0, 1, 0, 0, 0, 1. And then the parity, the transpose, which will be 0, 1, 1, 1, 1, 0, 1, 0, 1. Perfect. Now, we need to take the transpose of the generator matrix. So the transpose of the generator matrix is going to give us 0, 1, 1, 1, 0, 0, then 1, 1, 0, 0, 1, 0, and 1, 0, 1, 0, 0, 1, right? That is the transpose. And here, we also take the transpose of the parity check matrix, which would be 1, 0, 0, 0, 1, 1, then 0, 1, 0, 1, 1, 0, then 0, 0, 1, 1, 0, 1, right? So the next thing to do is to multiply this by this. So H times G transpose, or the transpose of G, will now give us 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, then 0, 0, 1, 1, 0, 1, times this operation, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, right? So this is going to give us something. And here, we also want to perform G times H transpose. So let's G 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, times the transpose, which is 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1. Then we have this. So let us multiply. So at this point, we now have, okay, let's use this point. Will be sufficient. That's this row times this column. So that will be 1. Okay, no, this will be sufficient. So let's do it here. This will give us 1 times 0, 1 times 0, plus 0 times 1, plus 0 times 1, plus 0 times 1, plus 1 times 0, plus 1 times 0. So that's what we have in the first instance. And then the next is 0 times 1 times 1. If you observe any oversight, please draw my attention to it. Then 1 times 1, 0 times 0, 1 times 0, 1 times 1, plus 0 times 0. Then this one now is 0 times 1, plus 0 times 0, plus 1 times 1 plus 1 times 0 plus 1 times 0 plus 1 times 1. So what are we going to get here? This is 0 plus 0 plus 0 plus 0 plus 0 plus 0. That is going to give us 0. Now, this 0 plus 1, that's 1, plus 0, 1, plus 0, 1, plus 1, 0, plus 0, 0. Then it's going to give us 0 plus 0, 0, plus 1, 1, plus 0, 1, plus 0, 1, plus 1, then that will give us 0. So we already proved that this is correct, okay? So it means this is a transpose of, this is more like an inverse of this in the binary field. Now, let us, well, it's a transpose. No, let's not use the word inverse at this one. But it's more like creating a reversal, okay? Now, then this also is going to be 0 times 1, that's 0 times 1, plus 1 times 0, times 0, plus 1 times 0, plus 1 times 0, plus 0 times 1, that's 0 times 1, plus 0 times 1, 0 times 1. Then this now is 1 times 0, 1 times 0, plus 1 times 1, plus 0 times 0, plus 0 times 1, plus 1 times 1, plus 0 times 0. So the next is 1 times 0, plus 0 times 0, plus 1 times 1, plus, so we're on the fourth one now, right? 0 times 1, plus 0 times 0, plus 1 times 1. So here, once again, we have 0 plus 0, this is 0 plus 0, plus 0, 0 plus 0, plus 0 plus 0, so this is 0. So this is 0 plus 1 is 1, plus 0, 1, plus 0, 1, plus 1, 0, plus 0, 0. And then this is 0 plus 0 is 0, plus 1 is 1, plus 0, 1, plus 0, 1, plus 1, 0. So we just proved this, right? This is correct. Okay. So now that we have this, then we can now conclude that yes, the parity check matrix times the transpose of the generator matrix is the same as the generator matrix times the transpose of the parity check matrix is the same as 0. Okay. And now you see that we also have that C, which is the code word, is the same as MG, right? So if we should multiply through, let's say by CH transpose is equal to MG H transpose, then what are we going to get? This is going to be the same as 0. So it means that should we multiply the code word by the transpose of the parity check matrix, we should have a 0. And once we have a 0, it means that there is no error in the received code word. Okay? So intuitively, when we have the message vector sent into the generator matrix, then we are going to have the code vector or code word, right? Now, when we now have this code vector sent into the parity check matrix, sorry. Now, what we should get is a null vector, is 0. Okay. And in order to correct for errors, we could have different kinds of codes, single parity check codes, which could be either even or odd. That's quite basic. So if, for instance, I have 1, 1, 0, 1, 1, so we have the total number, the number of ones says even, 1, 2, 3, 4 ones is even. So if I should add a redundant bit of 0, so it means we have 1, 2, 3, 4 ones. So this is even parity. So what if I still have the 1, 1, 0, 1, 1, and I decide to add a 1 as the parity check bit? So the total number of ones says now 5. This is odd parity. Okay. And recall that we add redundancy largely because we want to correct for errors. So it could be repetition code. So I want to transmit 1011. So I put this in the block. Then I transmit 1011 again. I put this in another block. I transmit 10111. So should I receive at some point 3 of these? Let's say I transmit again 11011. So these are different blocks. This is repetition code. So what if I now receive 11011, 1001, 11011, 11011? I can tell based on what I have received that what was transmitted is 11011. So that's another way of making corrections. But in as much as we attempt to do this, there is a metric we can use to determine the number of bits that can be corrected, which is the minimum distance requirement. Okay, you must have heard that. So let us quickly look at that. So we want to design codes. So for us to be able to tell, oh, this particular code can correct 1 error, 1 bit in error, or T errors, or so how do we determine that? So we start with the Hamming distance, okay? Hamming distance. And then we now have to talk about the Hamming weight. Then we'll now talk about the minimum distance, okay? Minimum distance. Now, this minimum distance is an important metric. It's an important metric when it comes to error correction codes. Okay, so when we say Hamming distance, what do we mean? So let's assume we have 2 code words, C sub I and C sub J. We now say that if we have this, then the Hamming distance between the 2 code vectors is equal to the number of elements in which they differ. Okay, so in other words, I want to check that, say, C sub I is the same as 1011, then C sub 2 is the same as 1000. So what is the Hamming distance between these two? So technically, what we are trying to say is that the Hamming distance, okay, before I come back to that, then the weight, the Hamming weight is the number of ones, okay, in the code, number of ones in the code. So for CI equal to 1011, so the weight is 3. That's the Hamming weight, okay? Because I want to relate the weight with the Hamming distance. And C sub J I used to here, let's say J, is the same as 1000. So the Hamming weight here is 1, right? Is 1. Because we have just a single one here. So, and the Hamming weight is the number of ones, the number of non-zero elements we have there, okay? Number of non-zero elements. That gives us the weight, right? So now the Hamming distance is the weight of the modulo 2 addition of the two code vectors, okay? So the Hamming distance is the same as the weight of the modulo 2 addition of the two code vectors. So for us to be able to tell the Hamming weight here, so what do? We take the modulo 2 addition. So this plus this is 1, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0. So the weight of this modulo 2 addition is 2. So the Hamming distance between these two code words is 2. Okay? Now, if that is clear, then we now come to the minimum distance, which is an important metric when it comes to the number of errors that can be corrected or controlled by that code. And here we now have that the minimum distance of a linear block code is the smallest Hamming distance between a pair of code vectors. So in other words, when we look up the code book and we have different code words in this code book, so by the time we begin to compare the weight, the Hamming weight of all of these code words, the minimum, the least weight in this code book will give us the minimum distance. Okay? I don't know if that is clear. I'd love to hear from you. Is that clear, please? Is that clear?
Yes, sir. Hello,
Now,
sir.
yeah.
Okay, yes, we are following you, sir.
Okay. Now, if that gives us the minimum distance, then let's now come back to our NK code. So if we now come back to our NK code or linear block code, we now say that this linear block code can actually correct all error patterns of weight T. So this NK linear block code can correct all error patterns of weight T if and only if the Hamming distance between these two code vectors is greater than or equal to T, 2T plus 1. And here we now have that T will be the same as D, where this Hamming distance is the minimum distance, D mean, then T will be the same as D mean minus 1 divided by 2. So this should be less than or equal to this. Okay? So once this reverses, so we can put this also as this if we want to bring D mean out minus 1. So this is the minimum distance. Okay? And then we can now begin to talk about different kinds of codes, Hamming codes. Okay, so if for instance, so I'll just run through now. So if for instance, let's say we have Hamming codes. So Hamming codes form, a part of the family of NK block codes. let's say the earliest of such codes that could correct one error, okay? A single error, a correcting perfect code. So we have some properties, the block length, where we have the integer m greater than or equal to 3. So we say that the block length n is the same as 2 to the power of m minus 1. Then the message bits k is the same as 2 to the power of m minus 1. And then the parity n minus k is the same as m, okay? Then I think in our earliest video, we talked about cyclic codes, and they form a subclass of the linear block code. And we say that a cyclic code or a code is said to be cyclic if it satisfies the linearity property and the cyclic property. And we already know what the linearity property is, that the sum of any two code words in a code is also a code word. And now the cyclic shift of a code word is also a code in that code word. Then we have quite a number of advantages and disadvantages. We want to take note of them for cyclic codes. So we have a number of advantages. And have its advantages. So the first of the advantages is that the error correcting and decoding methods of cyclic codes are simpler and easy to implement, okay? And this method or the methods eliminate the storage needed for lookup tables. We'll see some of those things much later. The encoders and decoders for the cyclic codes are also simpler compared to non-cyclic codes. Then we have that cyclic codes also detect error bursts, you know, and then what else? They also have a well-defined mathematical structure that, that permits higher order correcting codes. They also have easy syndrome. And we have quite a number of standardized cyclic codes, the cyclic redundancy check codes, 32, 8, and all of that. But a major disadvantage is that the error correction is a little complicated. Since the combinational logic circuits in the error detector are complex. So here they use combinational circuits, but we already know for block codes it's combinational circuits, but the convention and the structure to achieve the cyclic shift alongside linearity is quite complex. Okay. And then we also have that the cyclic codes are well suited for error detection. Okay. You know, we have error correction, error detection, but the cyclic codes are well suited for error detection. Okay. And we now see that a binary NK cyclic redundancy check code are capable of detecting the following error patterns. Number one, error burst. N minus K or less, okay? Then we also have a fraction of the error burst, okay? Of length N minus K plus 1. And there we have that the fraction equals 1 minus 2 minus N minus K minus 1, okay? And then we also have, as a third point there, a fraction of error burst of length greater than n minus k plus 1. So here, the fraction is the same as 1 minus 2 minus n minus k plus 1. Then we also have all combinations of dmi minus 1 or fewer. Then we also have all error patterns with an odd number of errors if the generator polynomial g of x code has an even number of non-zero coefficients. And then we have some properties of the bus Konduri Opwingen. That's BCH codes. So we have the block length to be the same as 2 to the power of m minus 1. Then the message bit is n minus mt. And then the minimum distance is greater than or equal to 2t plus 1. So here, for any integer m and t, for m greater than or equal to 3, we have that we have the BCH to correct for errors t, for which t is less than 2 to the power of m minus 1 over 2. So in other words, each BCH code can correct for t errors, unlike the Hamming codes that can correct for single errors. So this can detect and correct up to t random errors per code word, okay? And t is the maximum number of detectable errors, as we already mentioned. So in other words, BCH are cyclic codes. Going by the type of errors that can be corrected by cyclic code. And then a special type or an important subclass of BCH is the Rich-Solomon codes, okay, which we use most of the time in some of our communication system, and you see them in a lot of publications, Rich-Solomon codes. And for the Rich-Solomon codes, we have that the block length is the same as 2 to the power of n minus 1 symbols. Then we have the message size to be k size or k symbols. Now, the parity check n minus k is the same as 2t symbols. And then the minimum distance is the same as 2t plus 1. Okay? And now, there are a few examples, you know, in the previous videos. I may not want to go into in solving polynomial generator matrix and all of that, and doing and developing your syndrome, and then resolving a few details and all of that. Okay. Now, I would love to leave that for us to, you know, to play with. Now, let's come to syndrome, okay? Let's come to syndrome. Now we know we can generate these codes, okay? And we have some lengthy examples, which I may not want to go into, okay? But should I? Well, I think the examples we have in the block codes is quite explanatory, okay? So you want to look that up, and if need be, we'll make a review, okay? But now, an important part I want to mention is the syndrome, okay? Syndrome, okay, that's right. So if we use generator matrix to encode or generate our code words, then through syndrome decoding, we are able to decode. So I already explained this, how this works. So we already know that the code word is the same as MG. And then we also know that HG transpose is the same as GHT transpose, same as 0. So if what we receive is the same as the code word plus the error introduced by the channel, then the syndrome is the same as the received code word times the transpose of the parity check matrix. So hence, the syndrome will be the same as C plus E, HT, which is the same as CHT plus EHT. And we already know that C is MG, HT plus EHT. So here, we already know that this is equal to 0. Okay, GHT transpose is 0. So the syndrome will be the same as 0 plus EH transpose. Okay, so when there is no error, when there is no error in the received sequence, then EH transpose will also be the same as 0, so that the syndrome will be the same as 0. So now, going by this, where the syndrome is the same as EHT, it implies that the syndrome depends only on the error pattern, okay? Only on the error pattern, because that's what it means here, and not on the transmitted message, okay? Now, another property of syndrome states that all error patterns that differ by a code word have the same syndrome, okay? And once we analyze that, then we still come back to this expression. Now, we could quickly look up an example, okay? So now, let us take our parity check matrix to be 1, 0, 0, 1, 0, 1, 1, which you may have developed, if you were given a polynomial. That's an example. The example I skipped, 0, 1, 0, 1, 1, 1, 0, and then 0, 0, 1, 0, 1, 1, 1. Okay, we have this. And here we have that we received 1, 1, 0, 1, 1, 0, 0. So let us do syndrome decoding. So this is what was received, right? We want to check, given this parity check matrix based on the generator polynomial we used to design the generator matrix, and this parity check matrix, you look at it, we have the identity matrix here, and then we have the transpose of the parity check matrix. So from this, we can also extract this property, take the, then get the parity matrix, then derive the generator matrix. But here, we already have that the syndrome is the same as ROH transpose. So if we do this, so that's 1, 1, 0, 1, 1, 0, 0 times 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0. and 0, 0, 1, 0, 1, 1, 1, right? So once we do this, so we're going to have 1 times 1 plus modulo 2 addition, 1 times 0 plus 0 times 0 plus 1 times 1 plus 1 times 0. I think I'm short of space here, so let's wipe this. Let's manage the space. Sorry for that. Love it to be on one line. So we have 1 times 1 plus 1 times 0 plus 0 times 0 plus 1 times 1 plus 1 times 0 plus 0 times 1 plus 0 times 1. Then the next, this times this, that's this times this. So that will be 1 times 0 plus 1 times 1 plus 0 times 0 plus 1 times 1 plus 1 times 1 plus 0 times 1 plus 0 times 0. Then we have 1 times 0 plus 1 times 0 plus 0 times 1, 1 times 0 plus 1 times 1 plus 0 times 1 plus 0 times 1. Okay. So now that we have this, then this will be the same as 1. This is 1 plus 0 plus 0 plus 1. That is 0 plus 0 plus 0 plus 0. So we have 0. So this is 0 plus 1. That's 1 plus 0, 1 plus 1. That is 0 plus 1, 1 plus 0, 1 plus 0, 1. Okay. Then this is 1. This is 0 plus 0 plus 0, 0 plus 0, 0 plus 1 is 1 plus 0, 1 plus 0, 1. Whoa. So it means it is a non-zero syndrome. So it means that this was received in error. Okay, but how do we tell the location of the error? Now the syndrome tells us that. So with this, we now have to come back to the parity check matrix. And once we come back to this parity check matrix, either this or the transpose, we now look for, if we are using the parity check matrix, we look at the column that corresponds to this. But if we are using the transpose, we look at the row that corresponds to this. And the row that corresponds to 0, 1, 1, 0, 1, 1, this is it here. Which is 0, 1, 1, which is this, right? And that is, this is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5. The 5th bit is an error. 1, 2, 3, 4, 5. 5. This is an error. Okay, so it means that the actual bit that was transmitted is 1, 1, 0, 1, 0, 0, 0. Okay, this fifth bit. And now if we should replace that, if we should replace this with a 0, that's this one. So let us, instead of reworking this, let us look for where we had to multiply this in all of them. So in this case, that is 0 times 0, which is this, right? 0 times 0. So, well, everything is still 0, correct. Then here, that's this point. So this is going to be 0 times 1. So that will be 0. So we have 1 here. We have 1 here. So 0 plus 1, 1 plus 0, 1 plus 0, 0 plus 1, 0 plus 0, 0, 0, 0. So this now will give us, this now is 0. And then this point here is 0 times 1, okay? So here is now, this is 0, this 0, this 0, this 0, this 0, this 0, 0. So everything now have reduced to 0, 0, 0. So the syndrome is now all zeros to tell us that this is the actual correct, the originally transmitted bit sequence, okay? So you now see that with the syndrome, we are able to detect single bits for the Hamming code. But now, this brings us to another important metric, which I would love you to take note of, okay? Because if you consider what we have here, that is the syndrome, we have that the syndrome is the same as the received bit sequence times the transpose of the parity check matrix. So once we take note of this, you will see that if the syndrome is 0, it implies that the received code word is correct. It has no error. So with syndrome decoding, therefore with syndrome decoding, an NK linear block code can correct up to T errors per code word if N and K satisfies the Hamming bound. And what is that Hamming bound? We have 2 to the power of K minus 1 greater or equal to sigma I equal to 0 to T N combination I. And this could also be written as sigma I equal to 0 to T N combination I, where I takes on values from 0 all the way, right? And here Q is the same as the parity check bits, which is N minus K, okay? So I want you to take note of this expression because for the block code, in this case, at what point do we experience equality? So equality we hold for perfect codes. So if, for instance, we know K, we know Q is the same as N minus K. So if, for instance, 2, let's check the column, 2 to the power of N minus K minus 1 is the same as sigma I equal to 0 to T N combination I, we say this is a perfect code. And I also want you to note that the Hamming bound is necessary, but not sufficient for the construction of T error correcting linear block codes. It is necessary, but it is not sufficient. And now we are going to see that. Now, the Hamming bound. Let's look at the Hamming bound. Because we are going to use this to solve some problems, very important problems. So you want to take note of this if you want to take note. Now, the Hamming bound. So we said that in coding, the inequality 2 to the power of q minus 1, which is greater or equal to the summation of I taking on values from 0 to t and combination I, is related to the construction and performance of error correcting codes. Okay, this is related to the construction and performance error correcting codes. Okay, and so with this, we are able to determine the parameters of a code that can correct T errors. Okay, so we use this to determine the code that can correct T errors. So from this, we can say that the Hamming bound is often encountered when deriving the parameters of a code that satisfies, you know, the sphere packing bound. Okay, we can also call the Hamming bound as the sphere in bound. And for us to be able to explain this in context of the linear NK codes, so let us take things in base, 2 to the power of q minus 1. So this now represents the total number of syndrome in a linear block code. Okay, and here we know that Q is the same as the number of parity bits. So 2 to the power of n, so 2 to the power of n minus k minus 1 is the total number of syndrome in that linear block code. And then this summation I taking on values from 0 to t and combination I is the volume of a Hamming sphere. Of radius t around a code word. So this volume is the number of distinct error patterns that can be corrected, okay? So this volume is the number of distinct error patterns that can be corrected if up to T errors occur. Okay? So we know the total number of syndrome to be 2q minus 1, which is the same as 2n minus k, 2n minus k minus 1, right? because Q is N minus K. So if, sorry, Q is minus 1, is minus 1, right? Yeah, N minus K minus 1. So this is, like I already said, total number of syndrome in the block code. So for a code to correct up to T errors, the number of distinct patterns that can be corrected must fit within the space of possible syndrome. And this leads to the sphere packing bound, which is the same as the Hamming bound, given as the summation of I taking on values from 0 to T and combination I, which is less than or equal to 2n minus K. Okay, this is the sphere packing bound. But there's a caveat here because you can see we don't have minus 1 because the 2 to the power of n minus K is actually the number of distinct syndrome. In an NK linear block code. Okay? So, now that we already know that this is the parity, for simplicity, we often consider codes where the number of parity bits Q is such that 2 to the power of Q minus 1 is an upper bound on the distinct number of syndrome. Hence, the sphere packing bound now reduces to sigma I equal to 0 to T n combination I n minus K minus 1, which is the upper bound, okay? Considering 1 extra bit for all 0 syndrome. Now, we are going to play with an example of this, much later, okay? So if we do not have the time to do that here, then we'll resolve that, probably in the tutorial set. And if you look up the other video, we actually solved a problem where we had n greater or equal to k plus log to base 2 n plus 1, that you should show that the Hamming bound is given by this, okay? Just show that the Hamming bound is given by this when we have, I want to show this, show that n is greater or equal to this for the nk code when we have that the Hamming bound is given by T I equal to 0 to T and combination I. Okay, so we did this, we already solved this. But there's one part of this problem we did not solve, which was to construct a code. So I think I'll find time to solve that, okay? So you have that, it's very important, okay? Now that we have looked through this, then let us look briefly into the convolution codes, okay? So we just know we concluded all of those aspects. Now, the lecture note we also have on convolution code is quite comprehensive, okay? But I will just run through. We already made mention that here we need memory, okay? And in the lecture note on convolution code, we actually covered some techniques that can be used to achieve convolution codes, okay? Where we talked about the polynomial matrix method. We talked about the scalar matrix method. We also talked about the shift register method. Then we talked about the tree diagram method. And then we talked about the trellis method, okay? Now, I would love you to review all of these because here we use the, our major interest is the Galois field, right? Okay, GF2, that's our major deal, okay? So, and we're able to do some manipulations and all of that for both the polynomial scalar and all of that. So I would love to jump right quick, excuse me, into the shift register method, okay? Because they are all self-explanatory, really. Yeah. Took our time to detail all of those, okay? So let us look at the more practical system where we now have to use the shift register, okay? Now, so because we are really running behind schedule, okay? So let's look at the shift register method. Now, so I'll move straight to the shift register method. So you could take a quick recap on what we have done or what we did already, the lecture notes. Then if you have any questions, do just ensure you forward them to me, then we will review them, we could have a follow-up lecture on those. Now, shift register method. So we know that convolution codes are generated by transmitting data sequence through shift register, okay? And here we could have one or more shift registers. And the idea is that if we consider an NK convolution code, for instance, here we know that, let's say, let's just imagine a 2 by 1. So where n is 2, k is 1. So here we can tell the rate, which is k over n, which is 1 over 2, okay? So we have a half rate or a 1/2 rate convolution code here, 2 by 1 convolution code. Now, if for instance, it is a 3-stage convolution code, the number of registers, shift registers, tells us the number of stages. So S1, S2, S3. So here we are looking at a 3-stage, is the encoder, right? A 3-stage encoder. Okay, and we know it's half rate, right? It's a half rate convolution encoder. And now if we have the connection diagram to be something like this, so we have for this, given the input, so we have 2 outputs. So S1, S3 gets into this, and let's say S1, S2 gets into this. And then let's assume we have a switch to switch between these, okay? So let's say this is switch, okay? So this here we have the encoded output. Then it's a switch where we have 1, 2. So here we have V1, V2. Those are the 2 symbols, okay? And then here we have the input. Now, the constraints in this case for your convolution codes, okay? Now, we know it has memory, right? So the memory, okay, let's just, let's take this quickly. The memory is usually given as the degree, the maximum of the degree, the polynomial degree of the generator matrix, for instance. Then we have the constraints, K, which is the same as the memory plus 1, okay? And this is the size of the shift register in the memory encoder without feedback. So it implies the number of stages needed for the combinational logic to produce that output bit. Okay, that is the constraint. Now, if we have this, so it means that the memory will be the same as k minus 1. And here we have k to be the same as the number of stages, right? Which is 3, as we just mentioned. So the memory here will be 3 minus 1. M will be equal to 2. So for this 3-stage register, we can tell that the memory is 2. So you know that the error correcting capability is related to the constraint length, which increases with longer length. So the more the shift registers, then the longer the length intuitively. And then that also tells the error correcting capability of this code, because the convolution encoder is used to encode in such a way as to correct for burst errors. So the longer the stages, then the longer, or better still, the better, or the more bits in error, let's put it that way, we'll be able to correct. So this coder produces 2 outputs as we have in this connection diagram. Okay, so it means that in this case, the adder, we can use the adder here to generate our output, the combination, okay, the combinational logic. Okay, so let us dive straight into resolving this. The first stage of the shift register holds a bit. So once we feed this, I already explained this earlier. So whatsoever is in S1 moves to S2, whatsoever is in S2 moves to S3, and whatsoever is in S3 drops. Okay? Then, with this, we can now provide a little analysis here. Let's do this. So it means that if the original state, for instance, is all zeros, so let's assume we start with all zeros. 0, 0, 0. This is the original state. Okay. Now, let's assume if we are given the input sequence. For instance, the input sequence, let's assume it is 1, 1, 0, 1, 1. Let's just take this. So it means that once we feed 1 into this, the original state. So if we feed in 1, so it means that we are going to have 1. So this moves, this becomes 0, 0. Now, the next, this now becomes our initial state for the next bit, okay? So it means that if this becomes the initial state for the next bit, our next bit is 1. Once we feed that in, so we're going to have 1, this one shifts, then that 0 shifts, right? So if this becomes the initial state for the next input, which is 0, so it means we have a 0, then the 1 shifts, then that 1 shifts. Then the next, then this becomes the initial state for the next bit where we have a 1. So it becomes 1, the 0 shifts, then this 1 shifts, then the last one here is dropped, right? Then this becomes the initial state for the final bit where we have a 1. And then once that one fits in here, this one moves, and then the 0 moves, then the last one drops. So this is what we are going to get. So we can now put up the table, the lookup table. Now, in putting up the lookup table, let's check this column. Done this first. We have the input. Then we have our shift register 1. So straight lines. This then shift register 1, shift register 2, shift register 3. Then our input, our output V1 and V2. Okay. So we have 1, 1, 0, 1, 1. That sounds good. That looks good. So this is our input. This is shift register 1, shift register 2, shift register 3. Then this is output V1, V2. So this is the output. Good. Now, it means that when we feed in 1, then shift register 1 takes in 1, and then we have 0, 0, 1, 0, 0. Then when we feed in the next one, we have 1, 1, 1, 1, 0, right? Then when we feed in 0, we have 0, 1, 1. And then we feed in 1, we have 1, 0, 1. Then feed in the next one, we have 1, 1, 0. Okay. So now we are going to do something here. Now, when we feed in this all the way, okay, we see that at this point, what drops here? If we compare all of these, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1 drops here. And we have 0, 0, 1, 1, 0, 1, 1 drops here, right? Yeah. So, but this is what is useful here. So we now have to figure out the output, V1 and V2. So there's a connection diagram. V1 is given as the modulo 2 addition between X1 and S3. While V2 is given as the modulo 2 addition between X1 and S2, right? So with this, from the connection diagram, we've gotten the relationship to derive V1 and V2. So V1 is S1 plus S3. This plus this is 1. This plus this is 1. This plus this is 1. This plus this 0. This plus this 1. Okay. Then V2 is S1, S2. S1, S2. This plus this is 1. This plus this is 0. This plus this is 1. This plus this is 1. This plus this is 0. Right? Good. So going by this, it means that when 1 is transmitted, the output is 1. So we can now develop, we have our input, we have the input sequence, then we have the output, right? So going by this, by the shift register technique, when 1 is transmitted, we have 1, 1, 0, 1, 1. When 1 is transmitted, the output is 1, 1, when the next one is transmitted 1 0, and the next is 1 1, the next is 0 1, and the next is 1 0. Okay, so we are going to validate this using the state diagram approach. Okay, now let's just put this on a clean chart page. So from the shift register, so we're going to play with the same example. So what did we get from the shift register? So from the shift register, we were able to get for input sequence and output sequence. For 1, we have 1 1. For 1, we have 1 0. For 0, we have 1 1. For 1, we have 0 1. And for 1, we have 1 0. Yeah. So let us look at the state diagram approach to see if we'll arrive at the same thing. Now, generally, looking at the connection diagram, we could have as many stages, okay? But for the state diagram approach, we have to take note of the end stage, registers used, and then from this, we cannot tell the number of states, the states. So the state will be the same as 2 to the power of n minus 1. Okay, so in this example, we have 3 stages, okay, 3 stage, because we have 3 shift registers, right? Which is the same as the constraint. So in other words, we are going to have 2 to the power of 3 minus 1 states, which is 2 to the power of 2. Here we are going to have 4 states. This is very important, okay? So for us to be able to generate the state diagram from the connection diagram, the state table will have to be developed. So we need to develop the state table. So for us to be able to do that, so I'll just, let's take a straight line again. So here we have the state. Have the transition here. Shift register 1, shift register 2, shift register 3. So I'm going to So now we have the initial state. Then we have the state and state transition. Okay. Then we have our shift register 1, shift register 2, shift register 3. We have V1 and V2 from the connection diagram. We also know that V1 is the same as X1 plus S3, and V2 is the same as S1 plus S2. Now, here we have been able to establish that we have 4 states. So if we say that the states are A, B, C, D, then these states have to be related because each state will be able to emit a 0 and 1. Each state should be able to emit a 0 and 1. This state should be able to emit a 0 or 1, while this state should be able to emit a 0 or 1. Okay? And then for us to be able to arrive at this conclusion, then each state have 2 possible outcomes. Hence, the total number of outcomes here would be 8. That would be 2 times 4, right? Which is equal to 8 possible outcomes. So like in the previous example we worked, for an all 0 input, for instance, the state table will be something like this. We have all 0, 0, 0, 0. Okay? But now, for us to be able to establish this connection, so we have 4 states, A, B, C, D. So it means that A, we have to connect to either A or B. And this can either emit a 0 or 1. Then it means that B should be able to connect to C or D by convention. This can either emit a 0 or 1. Then C should be able to connect to A or B. Then this can emit a 0 or 1. Then D should be able to connect to C, D, right? Which can emit a 0 or 1. So once we take this, so if the initial state is all zeros, and then we plug in a 0, so it means that this 0 will take on the first bit, then these other zeros will be shifted, and the last one drops. What if it's a 1? So it means that this first portion will take on a 1, then the 0, next 0 shifts, and then this 0 shifts, then the last 0 drops. So if 1, 0, 0, let's draw this. 1, 0, 0. Let's say 1, 0, 0 is our next. So 1, 0, 0, right? So let's take 1, 0, 0 is now our initial state for the next state. So once we plug in a 0 here, 0, if C emits a 0, then this one shifts, then the 0 shifts, then the last 0 drops. Then what if a 1 is emitted? So this 1 shifts, then this 0 shifts, then the last 0 drops, right? Then in this case, by convention, say the initial state here is 0, 1, 0, 0, 1, 0. Then once a 0 is emitted, so we have 0 shifts, then this 1 shifts, then the last 0 drops. What if it's a 1? So we have a 1, then the 0 shifts, then the 1 shifts, then the 0 drops. Then here, we say the initial state by convention, then we're going to look at a trick here now. After this, 1, 1, 0. So now 0 is emitted first, so this 1 and 1 shifts, and then the last 0 drops. So then 1 is emitted, then we have 1, 1. Now, if you compare what we have here, you will see that this is similar to the truth table when we have 2 to the power of 3 equal to 8, where we have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 4 zeros, 4 ones, right? So this is consistent with our regular conventional truth table. Now, by using this, V1 will be S1 plus S3. So that's going to give us 0, is going to give us 1, S1 plus S3. This is going to give us 0. It's going to give us 1. It's going to give us 1. 1 plus 1 is 0. This is going to give us 0. This is 1. 1 plus 0 plus 1, 1. Then 1 plus 1, 0. Then V2 is S1 plus S2. 0. This is 1. This is 1. This is 0. This is 0. This is 1. This is 1. 0 plus 1. 1 plus 1 is 0. So we have 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Now, the state diagram now follows directly. So it means that we have 4 states. We have A, then we have B, we have C, and then we have D. Okay. Now, the first thing here is that A leads to A. So there's a connection. A connects to A. And when that happens, what is emitted is a 0. So let's plug in a 0 here. This is 0. And then the next thing is A, state A moves to state B. And once that is done, we have something like this, right? And what is emitted is a 1. So 1 is emitted here. And then the output for this is 0, 0. So let's plug in the 0, 0 bracket. And then the output for this from state A to state B is 1, 1. It's 1, 1, right? Then we have state B moves to state C, and a 0 is emitted. A 0 is emitted. And what is the output? 0, 1. And then we have B, state B to state D, right? Then 1 is emitted. And what is the output? 1, 0. 1, 0. Then the next thing now is that state C, from state C, we move to state A, back to state A, and a 0 is emitted. A 0 is emitted, and the output is 1, 0. And then from state C, we move back to state B. 1 is emitted. And what is the output? 0, 1. Then the next thing here is that from state D, we move to state C. A 0 is emitted. And the output here is 1, 1. And then from state D, we move back to state D. And 1 is emitted. 1 is emitted. And the output is 0, 0. So let us use this now to decode the sequence. So we have the input sequence 1, 1, 0, 1, 1. Okay. Now, when 1 is emitted from state A, we move to 1 is emitted. So if 0 was emitted, we move from state A to state A. Since 1 is emitted, we move from state A to state B. Okay. So we are going to move this way. And then the output is going to be 1, 1. So when 1 is also emitted from state B, we can either move from state B to D or to C. So when 0 is emitted is C. So, but 1 is emitted, so we are going to move to D, right? And the output is 1, 0. And from D, 0 is emitted. So if 1 was emitted, we are moving from D to D. So since 0 is emitted, we are moving to C, right? And the output is 1, 1. And then from C, 1 is emitted. So if 0 was emitted, we are going back to A, but since 1 is emitted, we are moving back to B. And that is 0, 1. And then from B, 1 is emitted. So we are moving back to D. And that is 1, 0. Now you see that using the shift register, this is what we got. And using the state diagram, we got the same output. Okay. Now there's also the tree diagram, which follows directly from the state diagram. I think I want to skip that. Then let us go to the interesting part, the Trellis diagram. I think that's where we'll call it a day today. Okay, so let's look up diagram. So another way the convolution encoder is designed is to use the Trellis diagram. And here we have that the number of states that we have to transcend is the same as 2 to the power of n minus 1, where n is the number of shift registers or the stages. So we have 2 to the power of 3 from the same example, 2 to the power of 4. So here we also have 4 states, right? We are dealing with 4 states. So in other words, it means that we are moving from state A to AB, then from state B, we are moving to CD, then from state C, we are moving again to AB by the convention we used earlier, and then from D, we are moving from C to D, okay? And here we use dots to represent the states. And the 2 branches emanating from each dot will now have to do with the uppermost and the lowermost, which will either tell us if it's emitting a 0 or a 1, okay? And if that is clear, we can just move straight in. So in this case, it means that we have A, B, C, D. So these are the states. We use dots to represent the states, right? So we can have as many of these dots depending on the length of the code we want to decode or encode, okay? So let's take it to this point. So it means that we can move from A to A. So let's use a different color this time. So we can either move from A to A, then A to B. So we can move from A to A or A to B. We can move from A to A, we can move from A to B, right? So we can have more states. And then we can either move from A to A or A to B. We can move from A to A or A to B. And then from the next state, okay, let's use a different color. We can move from, now we're at this point, so we can move from B to C or B to D. So we can move from B to C or B to D. We can move from B to C or B to D. B to D. We can move from B to C or B to D. We can move from B to C or B to D. Okay, all the way. And then from C, we can move from C to A or C to B. So we can move from C at this point. Recall that this is the same state. So I can't move from this to this. So I have to move to the next state. So from C to A or C to B, that same state. Okay. So I can move from C to A or C to B. So I can move from C to A or C to B. Then the next now, I can move from D to C or D to D. So this is, we're on the same state here. So I have to move to the next state, D to C or D to D. Then I can move from D to C, D to D. And equally move from D to C or D to D. Good. So now we want to decode, okay? Let's say we want to solve that same problem or some other problem. So now that we have generated this, then the state diagram follows directly. We have the same state diagram that we used before. So let's just pull it up again. So we have S1, S2, S3. Then we have V1, V2. So here we'll have 0, 0, 0. We have 0, 0. Where we have 1, 0, 0. We have 1, 1. Okay. Then where we have 0, 1, 0. Then here we have 0, 1. Where we have 1, 1, 0. Then we have 1, 0. Where we have 0, 1, 0. 1, 2, 3, 4, 1. 0, 1, 2, 3, 4. 0, 0, 1. We have 0, 0, 1. That will give us 1, 0. Then we have 1, 0, 1. Then that should give us 0, 1. 0, 1, 1. We already used this, we already derived this using in the state diagram approach 1, 1, 1. So I'm just repeating the 0, 0. Okay. So from this, recall that for state A, this AB, this either emits a 0 or 1, right? Then for state B, we move between CD, this either emits a 0 or 1. Then for state C, this is AB, this emits a 0 or 1. And then from state D, this is CD, this emits a 0 or 1. So now going by this, we can now populate this Trellis diagram with the encoder output so as to use this to decode. Now, for us to do this, we now have to observe closely moving from A to A, the output is 0, 0. So meaning the output of this lookup table may vary depending on the structure of the connection diagram. So you want to take note of that. So we have 0, 0 this way, 0, 0, 0, 0, 0, 0, 0, 0, based on the connection diagram. Then from AB, which emits a 1, so in this case, this emits a 0, okay? This emits a 0. This emits a 0. So when it emits a 1, we have this here, 1. It emits a 1. This emits 1. And the output is 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay? Then for B, when it emits a 0, we have 0, 1. So that is from B to C. So at this point, it emits a 0. It emits a 0 here. It emits a 0 here. It emits a 0 here. And the output is 0, 1. Then when it emits a 1, then it is 1, 0. So here it emits a 1. Emits a 1 here. Emits a 1 here. Emits a 1 here. That's from B to D. B to D. So that's 1, 0. This 1, 0. This 1, 0. This is 1, 0. This is 1, 0. Then from C to A, it emits a 0 here. It emits a 0 here. It emits a 0 here, right? And there we have 1, 1, 0. So this is 1, 0, 1, 0, 1, 0. Then, when it emits a 1, that's C to B. So here it emits a 1 here. It emits a 1 here. It emits a 1 here. And there we have 0, 1, right? This is 0, 1, 0, 1, 0, 1. And then from D to C, here it emits a 0, it emits a 0 here, it emits a 0 here. And the output is 1, 1, 1, 1, 1, 1. And in this case, it emits a 1 from D to D, D to D, D to D. So that is 0, 0, 0, 0, 0, 0. So now, if we now consider that 1, 1, 0, 1, 1 is transmitted. So from point A, we now have that 1 is emitted. When 1 is emitted, so we are tracing down. Right? Tracing down. So we have 1, 1 from the decoder. Then 1 is emitted again, so it means we are still tracing down. That's 1, 0. Then 0 is emitted, so it means we are tracing up this way. Then 1, 1 is emitted. Then from there, 1, so we are going this way. So that's 0, 1. Then from here, 1 is emitted. So when 1 is emitted, so we are coming this way. Okay. So that is 1, 0. I see that this is consistent with what we transmitted earlier. Now, what if there is an error? Say, rather than receive this, let's assume this is correct. So let's assume we now receive 1, 1, 1, 0, 1, 1, 1, 0, 1, 0. So it means that this particular bit is in error. Now, let us try to use the trellis diagram to see what the trellis diagram will do. That's why it's very, very powerful. So let's use a different color here. Okay, let's use this. So if, for instance, we want to do this, then it means that we have to move all the way. Okay, so it means at this point, everything is okay, everything is in order. Then we move all the way. Yeah, everything is still in good shape this way. Then everything is also in good shape this way. Then the next thing is 1, 0. This is 1, 0 here. So it means we are going to go upward, right? So once we get this way, going by what was received, now the next bit is supposed to be 1, 0, but we don't have 1, 0 here. It's 0, 0, 1, 1. So it's either it takes this part or it takes this part. Okay? So you now realize that at the end of the day, in decoding through this part, we are now going to have 1, 1. Let's wipe this. Now, going by this part, we are going to have 1, 1, 1, 0, 1, 1. Then we are now going to have on this part, this is 1, 0. Then on this part, we are going to have 0, 0. Or better still, we are still going to have 1, 1, 1, 0, 1, 1. 1, 0, 1, 1. Okay, on this part. That's one possibility. Then, if you look at it, we now have 2 bits in error on these 2 parts. Alternatively, this program may now want to also go through this route and come either this way or this way. Now, if it should come, now this is on this part, this is on this part. Now, if it should come on this part, so it means we are going to have 1, 1, 1, 0, 1, 1. Then what do we have here now? This part. And this is 0, 1, 0, 1. Okay. So in this case, we are not going to have, then on this final part, we are not going to have 1, 1, 1, 0, 1, 1, then 0, 1, 1, 1. Okay. Now, once we compare this relative to this again, then relative to what was transmitted, relative to what was received, you observe that, sorry, this is 1, 0. 1, 0. This 1, 0. Now, relative to what was transmitted, or relative to what was received, rather, this is what was received. You now see that here we are having 0, 1. So this is in error. and then 1, 0, this is also in error. Then once we compare with this last part, you see that this is in error, but this is correct. This is correct, this is correct, this is correct. Now you observe that by comparing all of these states that we have here, at the receiver, the part with single conflicts in this example will be the most likely part, because at the end of the day, going by the wrongly received bits, this does not even tally, and this does not tally. But this tallies with the original bits. Now, comparing all of these three parts, we have two completes, we have two completes, we have two completes. Here we have just one complete. So what the receiver does using the Trellis decoding system is to select the part that is most likely. And that is why it is called the maximum likelihood decoding algorithm. Okay? And hence, by comparing all of these parts, it is going to take this part with just a single complete, which tallies with what was transmitted. So with this, I would say, fine, we have done the needful in just running through what's it called now? Both convolution and block codes. So before we call it a day, there is one more aspect which I'm supposed to talk about, which is more complicated, which is the 7-step Trellis diagram. You know, I may mention it just in passing in case someone will want to say, well, but why are you not mentioning it? Since it's part of what we have in the videos, but it's already in the other video. But I may mention it in passing with one interesting example. But so far, any question, please? Any question, please? I would love to get your feedback before I move on, just to take one final example, and then we'll call it a day.
You can proceed, sir.
Okay. Okay.
But I have a comment at the end of the whole lecture.
Okay. Let's look at the 7-step Trellis diagram. Now, in this case, it's not different from what we just looked at, where we considered 4 steps, but that was rather simplified. And there you see that the encoder output was 2 bits. What if we now have to deal with encoder output that is more than 2 bits? Let's say 3 bits or more. And yet we have something like that connection diagram, but this time with 3 outputs. So let's consider this simple example. So let's use an example different from what we have in the other video. So let's say we have the shift register 1. Then we have another shift register 2. Then we have another shift register 3. Then we have this other here, and we have this other here. And then we have this other here. So let's assume these 3 shift registers are connected to output bit 3. And then these 2 shift registers are connected to output bit 1. And then these 2 shift registers are connected to output bit 2. Now, In the previous example, we literally consider the case where the code book contains 8 possible code words. But now we want to look at a code book that contains about 16 code words and 3 possible output bits, like we have here. So here we have the input. Now, since we also have 3 shift registers, then we can tell that the total number of states will be 4, right? That's 2 to the power of 3 minus 1, which is 2 to the power of 2, which is 4 states. But how are we going to map these 4 states among 16 possible code words? When we had just, 8 code words, at least we know each bit could transmit, each state could transmit a 0 or 1. But now, same thing here. Each state will be able to transmit, or better still, emit either a 0 or 1. But the point is, we now have to lump it up in 4s, right? So for us to have 4 states, then 16 possible code words divided by 4 will be equal to 4. So we are going to have 4 code words per state, right? So the transition or state transition will be in the interval of 4. So, and 4 code words can either emit a 0 or 1. So now I want to look at the 7-step Trellis diagram, okay? So I'll just walk through with this, and then we'll see how we'll be able to generate everything on this table. So we'll just try to maximize this. So we need some clean lines here. So let's say we have this, okay. Let's break this. So we are now going to have this. We need 16 possible code words. So we have 1, 2, 3, 4. Now have state A, then have a shift register 1, register 2, register 3, then we have input, have shift register 1, 2, 3, state B, have input, input 2, input 3. So let's label this. So we have our state. Okay. So we have the states. This state A. So we have our shift register 1, shift register 2, shift register 3. Then we have the input. Then we have shift register 1, shift register 2, shift register 3. Then we have state B. Then we have output bit 1, output bit 2, output bit 3. Okay. And now from this, output bit 1 is the same as S1 plus S2. Output bit 2 is the same as S2 plus S3. Then output bit 3 is the same as S1 plus S2 plus S3. Okay. So now we can move from state 0 in 2s to states 0, 4, and 4 bits can be in the same state. So it's either in 0, 0, 1, 1 to 0, 4, right? And then we move to 2, 2. Then here we have 1, the interval between 1, 0 and 4, 1, 5, right? Then we can move to 3, state 3. So it's still 1, 5. That's interval 4. Then we can move to state 4. That's 2, 6. And then state 5. It's 2, 6. Then we can move to state 6. That's going to be 3, 7. And then state 7 is going to be 3, 7. Okay. Now, just a regular distribution. So if all bits are turned on, that'll be 0, 0, 0, 0. That's for the 4, 2 to the power 2 to k, that's 2 to 4, that's 16. So I just want to drop down the truth table, right? 1, 2, 3, 4, 5, 6, 7, 8. Then we have 1, 2, 3, 4, 5, 6, 7, 8. We have 1, 2, 3, 4. 1, 2, 3, 4. 2, 1. 1, 2, 1, 2, 1, 2. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0. Good. Now, going by our previous analogy, if the inputs 0, 1, 0, 1, 0, 1, 0, 1, because we know we can only feed in the input with either a 0 or a 1 for a given state. So if we have to move from state 0 to 0 or state 0 to 4, then we can either input a 0 or a 1. Now, once we feed in the first shift register with a 0 or 1, so we're having 0, 1 all the way, right? 0, 1, 0, 0, 1. That's input 0, 1, 0, 1, 0, 1, 0, 1. Then what was held by the shift register originally is all 0, 0, 0, 0, 0, then 1, 1, 1. We move to shift register 2. So here we have 1, 2, 3, 4, 5, 6, 7, 8. That's what we have here. 1, 2, 3, 4, 5, 6, 7, 8. And what was stored by shift register 2 originally now moves to shift register 3. That is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. And what was held by shift register 3 is dropped. Then we now have to design the output or the output bits using this algorithm, right? The connection diagram. So for output bit 1 is S1 plus S2. So S1 plus S2, 0 plus 0 is 0, 0 plus 1, 1, this is 0, then this is 1, and this is 0, this is 1, this is 0, this is 1, this is 1, this is 0, this is 0, this is 1, then this 2 here is 0, this is 1, this is 0, this is 1, this is 0. Okay. Now the next is S2, S3. These two, S2, S3, that's 0, 0, 0, 0, and this is 1, 1, 1, and this is 1, 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 and this is 0, 0, 0, 0. Then the output the 3 is S1 plus S2 plus S3. This 0, 1, then that's 1, then this is 0, then this is 1, this is 1, then this is 0, this is 1, this is 0, this is 1, this is 0, 0, this is 1, this is 0, this is 0, and this now is 0 plus 1, this is 1, and this is 0, and this is 1. Okay. So now we have developed this. So the next thing is to design the Trellis diagram. Okay, in order, all the bits are correct. All the bits are correct. 0, 1, 0, 0, 1, 1. Okay. So now, in designing the Trellis diagram, then we have 7 states from 0 to 7. So we have 1, 2, 3, 4, 5, 6, 7, 8. So this gives us 0, 1, 2, 3, 4, 5, 6, 7. That's perfect. So we now have to document all the states. That's 1, 2, state 2. State 3. State 4. State 5. State 6, on and on, okay? So we can go on and on depending on the length of code words we want to decode. So now we want to design this just the same way we did the other. Okay, let's use this color. So now we have to move from state 0 to state 0, okay? So move from 0 to 0. Let's use straight lines. We want to move from 0 to 0, then to 0 to 0 to 0 all the way. And then we want to move from 0 to 4. So move from 0 to 4. 0 to 4, 0 to 4, 0 to 4, and 0 to 4. And here, what do? We now assign the codes. The output for 0 to 0 is all zeros. So this is all zeros, all zeros, all zeros, all zeros, all zeros. Then from 0 to 4 is 101. So this is 101, 101, 101, 101, 101. Then we move on to the next, which is from 1 to 0 and 1 from state 1 to 4. So we move from 1 to 0, 1 to 0, 1 to 0, state 1 to 0, 1 to 0, and then 1 to 4. You observe that we already locked this up, okay? So at every point in time, we get to lock them up, okay? Once we move between two states, you see they are locked up. Locked up. And then we can now include the output code. Here is 000. This is 000, 000, 000, 000, 000, 000. And then from 1 to 4 is 101. This is 101, 101, 101, 101, 101. Then we can now move from 2 to 1 and 2 to 5. From 2 to 1, 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 then 2 to 5, 2 to 5, 2 to 5, 2 to 5, then 2 to 5. Then we now include the code word from 2 to 1 and 2 to 5. So we have 0, 1, 1. So this is where we are. Then we have 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1. And then 2 to 5 is 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0. So well, this could be time consuming, but I will just try to do the needful. Okay, so now we have from 3 to 1 and 3 to 5. Okay, 3 to 1, 3 to 5. That's 3 to 1, and 3 to 1, 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 and then 3 to 5. So we already locked this up. 3 to 5, 3 to 5, 3 to 5, and 3 to 5. So then we include the output code. That's 0, 1, 1 here, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. And then here, then 3 to 5, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0. Then we move on to the next. Here, that will be from, we are done with 3. So we are moving from 4 to 2 and 4 to 6. So from 4 to 2, 4 to 2, 4 to 2, 4, 2, 4, 2. Then we have 4 to 6, 4, 6, 4, 6, 4 to 6, and then 4 to 6. And then from 4 to 2 is 1, 1, 1. So this is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then from 4 to 6 is 0, 1, 0. So this is 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0. Then now we have to move from 5. Okay, from 5 to 2 and 5 to 6. 5 to 2, 5 to 2, 5 to 2. And 5 to 2, that is locked up, so in order. 5 to 6 is also locked up. 5 to 6, 5 to 6, 6, and then 5 to 6. Good. So from 5 to 2, we have 1, 1, 1 here. This is 1, 1, 1, 1, 1, 1, 1, 1, 1. And from 5 to 6, we have 0, 1, 0. 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. Then we now move on to 63 and 67. So 63 and 67. From 6. Oh, that's straight line. So 63, 63, 63, 63, 6. Then 67, 67, 67, 67, and 67. And then we can include the output bit. That is 67 is here. That is 1, that's 63, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. And then 67 is 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. Then finally, I now want to move the colors of them. Let's use this. So we now want to move from 7 to 3 and 7 to 7. 7 to 3, 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 and then we move from 7 to 7 all the way up. Then we can now include the code words. That's from 73 is 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. And then from 7 to 7 is 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. Perfect. So let's assume here we received this. So let's assume we receive the following code words. Now, so let's assume we receive. So here we have 1, 2, 3. Let's just put 5. So let's assume we receive 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, for instance. We could go on and on, okay? Now, let us check what was decoded. And we are going to decode these based on their weights, okay? Based on their weights. Now, we already mentioned Hamming weight and Hamming distance. So the Hamming weight is just the number of ones, right? Now, the weight we are going to consider here is more like the minimum distance, okay? Recall we talked about the Hamming distance. So I'd rather call this the Hamming distance, but it is the weight of the Hamming distance because we now have to compare the difference between two codes, okay? Going upward or going downward, okay? Now, if a 0 is transmitted, so we have to start off from this point, okay? So 0, 0, 0 was sent. So now, but we have two possibilities. So we're going to follow the path with the least weights. So for the first instance, we have 0, 0, 0 transmitted. But we have two possibilities. So we have 0, 0, 0. So we're going to take the modulo 2 addition with this 0, 0, 0 and 1, 0, 1, 1, 0, 1. So what is the weight? This is going upward, and then this is going downward, right? So let's just put it that way, upward, downward, upward, downward. So here the weight is 0. Then here the weight is 1, 0, 1. The weight is 2. So here we have 0 over 2 upward weight, and or better still, the weight of the Hamming distance, right? So the Hamming distance is the weight of the modulo 2 addition, right? So this is more like using the Hamming distance, right? The Hamming distance, which is the weight of the modulo 2 addition between these two parts and comparing with the code that was received. So once we do that, we now check the part with the least weight, the shortest part, okay, in terms of the Hamming distance is going upward. So here we are going to trace this way. So we're going to go through this part. So the code that was decoded is correct. That was transmitted. There's no error for now. Then the next part now is to check 111, 111, 111. So from this part, it's either we go upward, which is a 0, 0, 0. We're going to check the distance, Hamming distance, or it comes down 101, 101. So this is 111, and then this is 0, 1, 0. So the weight here is 3, 1. So it's 3 over 1. So the weight, the distance, the shortest part is coming downward. So it means that the code here that was transmitted is supposed to be 101. So this was received in error. So we now want to trace downward onto this point. So the coded code word here is 101. So from this point, we now have two possibilities as well, but we received 111, 111, upward and downward. So going upward is 111 here, 111. Then going downward is 010, 010. So once we take the Hamming distance, this is 000, then this is 101. So that's 0 over 2. So it's 0, upward over 2. So we know the shortest path is upward, right? So we are coming this way to this point. So what was received is correct. Okay. Now, afterwards, excuse me. Now we can now check for the next where we received 110, 110. So from this point, we have two options, 0, 1, 0, 1, 1, 0, 1, 1, and then the next here is 110, 110. So once we take the way, this is 101 and this is 000. So that's 2, 0. So that will be 2 over 0. So it means we are taking it downward. Okay. Let me take it. Downward. Okay. And so we could go on and on and on, and I realized that the decoded word there is 110. So you see, with this, we can actually correct both errors. Here we corrected this error. And we can correct multiple errors. Hence, this is referred to as the Viterbi maximum likelihood decoding. Viterbi maximum likelihood. Okay, I think this is a good place to stop, and we could entertain a few questions. Any question, please?
Hold on, sir. Mine is not a question. I still want to plead because of this, the solved questions.
Okay.
If it's possible, I don't know how large the file is. I don't know if it's a video or it's a kind of PDF solved questions. If it's possible to drop it on the group, because it's very, very important because of these exams.
Okay.
But that is the real issue now. Okay. So I don't know how we can get it, since this one on YouTube is giving us challenges.
Okay, I think we should be able to resolve that. You need some tutorial questions, and then we should be able to resolve that. Okay. So that's not going to be a problem.